So thank you for coming to this presentation. I'm going to talk about a project we did at PeopleDoc Software, which is a custom logical replication system. So who am I? I'm a DBA at PeopleDoc. So PeopleDoc is an HR delivery software publisher. And as such, we have lots of Postgres database, and we have lots of Postgres needs. And also, probably like every company here, we are hiring. And so if you're looking for a job, you can apply to PeopleDoc. I've been working with Postgres for quite a few years now. I've been a small-time contributor with some features in Postgres. I've also written quite a few PostgreSQL extensions, working with foreign data wrappers, monitoring, and things like that. So the things I'm going to talk about is a problem we had. We have a problem at PeopleDoc is that we have a lot of transactional database. Each application has its own transactional database, and like most companies, we have a business intelligence team. And business intelligence people like to cross data. They want to have access to every piece of data that is available somewhere. So we have to federate that somehow. Our first solution to the problem, which is still used right now, was to federate this using foreign data wrappers. So what we did was we have sort of an empty shell database that uses foreign data wrapper to connect to every single transactional database. This was great for some time, but we ran into problems with that. The first problem is that performing joins across foreign data wrappers is quite expensive and quite time-consuming. So we had materialization, but that means that we have to refresh the data quite often. We considered a few solutions to this problem, one of these being using ETL. But the problem with ETL is that it's a problem of change capture. Change capture is usually done with triggers, and it's expensive on your primary server, on your transactional database. Ideally, you don't want your business intelligence needs to have any impact on your transactional DB. So what we wanted to do was use logical replication to do that. The project is codenamed Connemara because it's kind of a data lake. I don't really know what a data lake is, but I've been told it's when you have several rivers of data aggregating into some place, so it kind of fits. But let me know if you have a better definition of a data lake. So what we set up to do is use logical replication to federate several databases into one. The problem we have is that our transactional DBs sometimes have tables named with similar names. So we want to move every single source table to its own schema on the target database. And that's something that the built-in logical replication in Postgres can't do right now. Well, we could have used other logical systems based on triggers like Slowney and things like that. But remember, we don't want to have too much of an impact on the primary server. So we set up to build our own using PostgreSQL logical replication basic building blocks. What is great about this is that the hard part is done by Postgres itself. It's called logical role streaming, and maybe you're familiar with that. Maybe you've already toyed with logical decoder, role receivers, and things like that. And it's also the basic building block for the built-in logical replication. So using those building blocks, we set up to build our own. So why this presentation? Because we want to offer some insight into what it takes to build a replication system. And surprisingly, it's quite easy because Postgres does all the hard work for us. And it's also a preparation for when we will open source it. Right now, we haven't published the code, but it's something we want to do. The reason we haven't done it yet is because currently it's a bit messy, a bit too specific for our needs, but once it's generic enough and once we've got rid of some parts that are still tied to our proprietary systems, we will release that. And more importantly, it's to show what we learned building that regarding our logical replication working in Postgres, and maybe that can serve as an example if you have similar needs and want to build the same kind of thing. So I'm going to divide this presentation into two parts mostly. The first one will be about the Postgres features that allows us to build that. And the second one will be our actual implementation and how it works. So how does logical replication work in general? Well, probably most of you have heard about WAL, the write-ahead logging. This is used for physical replication and for logical replication. But for logical replication, the WAL encodes more information, such as logical operations. That means commits and inserts, updates, deletes, and everything you need to have a logical view of the changes done to your database. We're building on three fundamental key concepts. The first one is the one of our replication slots. Probably if you're using physical replication, you're already using replication slots. You have two kinds of replication slots, physical replication slots and logical replication slots. The goal of our replication slot is mainly with the physical one to keep WAL until they've been consumed. For logical replication slots, it offers some additional features. The second thing is the Decoder Plugin associated to the replication slot. And the third concept we are using is the one of a Replication Origin. That's also something that's built into Postgres that is not so as well known as the other ones, but it's really, really useful and makes life really easy when building such a system. The idea is to allow you to track progress of what has been replicated to the secondary server so that you know what to ask the primary server. So, if you want to use logical WAL streaming, you'll need to tweak the Postgres configuration. Most importantly, WAL level should be set to logical, otherwise you won't have any information in the WAL to perform logical decoding. The second thing is the replication slots. Its primary purpose is to keep the WAL segments until they've been consumed. And it also offers you monitoring out of what have been consumed or not. In the case of logical replication slots, you associate a logical slot with a decoder. So you can either use SQL to create your replication slot. That's when you do it manually. So you connect to your Postgres instance using a standard connection, and you call the SQL function pg create logical replication slot. But the second way to create a replication slot is when using the special replication protocol. And in the replication protocol, you have a special replication command that you can send on the wire to create a replication slot. Once your slot has been created, you can use a replication connection to consume the changes. So in that case, you issue the start replication command on the replication protocol, which will place the connection in the copy both mode. Copy both allows you to perform copy from and to the PostgreSQL connection. So if you're reading copy data in, you're getting the replication stream, and you can write feedback to this replication connection. This feedback allows you to inform the PostgreSQL servers that you have actually consumed the WAL and that it's safe to discard previous WALs. That's how it works to have the replication slot advance. So I said that the replication slot is used with Decoder Plugin. So the Decoder Plugin we are using is WAL2JSON. It's an open source decoder. It's been developed and it's in some use, and it's been packaged in the pgdg Debian repository, and that's why we chose it initially. And this plugin offers you a lot of options. What we use are several options, like include schemas to actually include the schema names of the table for which we are receiving data, and including the transaction IDs, the timestamps, the commit timestamps, and the ability to filter some tables that we don't want to replicate to the secondary server. So what this decoder does is just it takes a WAL stream and encodes it into one big JSON. And every time a transaction commits, you receive one big JSON with every change associated with this transaction. After that, it's up to you to read this JSON and do with it whatever you want, like replaying the changes to your target database. The third concept I would like to introduce is the one of a replication origin. So this allows you to track replication progress on the target database. You can consult replication origin in the system PG replication origin table. And it's quite easy to use. You have to set up the replication origin by first creating it using the appropriately named function PG replication origin create. You give it a name, which must be unique, of course. And then you can advance your replication origin position to the starting position in the LSN on the primary server. This is useful to know at the start when you start replication, from what point you need to start streaming WAL, because you can't replay a WAL from the beginning of the time, and you don't want to miss WALs and have holes from the start of your replication to the current time. And then after that, once you start replicating, you can use other functions. So you can tie your current session to a replication origin and then bind your current transaction to the replication origin with an LSN and a timestamp number from the source. What does that mean? It means that every transaction that you're going to play on the target database will be associated to a transaction timestamp and a position in the WAL stream from the source database. And when you commit your transaction, Postgres will keep track of this information and will know that you have replayed up to this level of WAL from the source database into your target database. That allows you to easily resume where you left off next time you connect and you start replicating things. Of course, if you roll back, Postgres takes care of that and doesn't advance this counter. It's really nice to avoid concurrency issues and two-phase commits and things like that, things that would be problematic to manage. So with these basic building blocks, we set up a quite simple architecture. We have 3 components. The first one is a base backup. Exactly the same way when you start physical replication, you need to start with a base backup, the base point on top of which you can start applying WALs. So we have a tool for that, which allows you to bootstrap your replication system at a given point in the WAL stream. And from then, you can start applying WAL records and keep a consistent database. The second component is the Connemara replication daemon. This is the one which actually connects to the source database, fetch changes from the Decoder plugin in JSON format, because we are using the WAL2JSON decoder, and then we'll write those changes to the target database. In a spool table, because we don't want to apply changes right now, we'll see why later. The third component is a replayer. It acts only on the target database and reads messages from the spool table and then applies them to the actual table. This is the part actually inserting, updating, and deleting data on your target database. So a small picture, I hope it's readable. So initially, we're using the base backup tool to dump the database and restore it on the target database. Then we have the replication daemon. We have one replication daemon by source and target copper. It will stream changes from the WAL stream on the source DB and copy them in a special table in the target DB. And then the third tool, the replayer, will consume message on the target DB and apply the changes from those messages to the actual tables. So first problem, the base backup. We have several problems to solve with a base backup. We want to ensure a consistent backup without losing any transactions, which means we have to know at which point in the WAL stream this backup was taken to be able to replay every WAL we need to have to avoid any loss of data. We also need to restore tables in the different schema, because remember, that was our first problem with the existing replication system. We need to restore tables in different schemas. And also, we don't want everything, because on our transactional workload, we have lots of indexes and maybe views and triggers and things like that that we don't need on an analytical system. Theoretically, it looks like the first problem is the most difficult one, but in fact, it's not, because PostgreSQL provides us with everything we need for that. So how do we ensure consistent backup? We initiate a logical replication connection. We create a replication slot using the create replication slot replication command. And we tell it to use our Decoder Plugin, wall-to-JSON, and most importantly, we use the export snapshot option. It's a default option, so you don't really have to specify it, but that means that once your replication slot is created, the snapshot of the current transaction will be exported. So this snapshot will allow you to connect and see exactly the data as it was when the replication slot was created. And this command returns you a tuple containing everything you need. So the slot name, since you provide it, you already know it, so it's not really important. The consistent point, that's the position in the world stream at which point the replication slot was created, and the snapshot name. Snapshot name will be really useful to see the same data. Maybe you've already know about exported snapshots. That's exactly how pgdump works. When you, I think the feature was originally developed for pgdump parallel mode. That's what pgdump does when you use it in parallel mode. The master process exports a snapshot, and then forks any number of processes which will use the same snapshot to get a consistent view of the data. So that's a good thing that pgdump is allowed to use an exported snapshot. So that's exactly what we do. And with this dump, we restore this dump on the target database, and now we have a dump taken at a known point in the world stream. And from that, we can start applying walls. Exactly like what you do when you take physical base backup when you want to use physical replication. Second problem was restoring in a different schema. As far as we know, there's no tool capable of taking your whole database and restore it into a different schema. We needed to do that ourselves, and what we needed to do was recreate every object in schema, for example, public from the database db1 to a new schema named db1 public on the target database to avoid name collisions. The first solution was to rewrite the dump on the fly using regular expressions, but now we had one problem more, as they say. It works well enough, but no, it didn't work well at all because, in fact, schema names tend to creep about everywhere in pgdump output. And actually, there are some things that we don't want to relocate. For example, our database 1 and database 2 might use the hstore extension. So we can't create the hstore extension only in the schema belonging to database 1. We can't do that. We need to keep this extension in the public schema because every extension can only be created once in a database. So that's what we, with that we had to tweak this a bit because we had to keep track of many things that we didn't want to rewrite. So we set up for solution number 2. Solution number 2 was to parse the dump, build an abstract syntax tree of every SQL statement, modify it, and emit the row. Thankfully for us, we have a great library helping us to do that, which is pglast, which allows us to build an AST, abstract syntax tree, rewrite it, and then emit the corresponding SQL. I don't think, no, it's not legible at all, but that's an example of an abstract syntax tree that you get from pglast. And from that, you can modify it as much as you want and then re-emit or deparse, like it's sometimes called, the resulting SQL. So in summary, with base backup, what we do is create a replication slot, fetch the associated snapshot, perform a pgdump, restore this pgdump with small tweaking, renaming the schemas and dropping things that we don't want in the process. And at the end, we are creating a replication origin on the target database to keep track of the point at which the dump was done. So for the next part, the replication itself, we know on the target database the point in the wall we need to resume from. So the second part is a streaming replication daemon. It's a small daemon in C. It's as simple and as stupid as possible. What we wanted to do is have as less impact on the primary server as possible, so we wanted to consume the WAL as quickly as possible to not have WAL piling up on the primary server. So how it works. Excuse me. We open a replication connection, we connect to the target database, and then we start the replication slot with the position fetched from the replication origin on the target. Every source database transaction is wrapped into a transaction on the target database, and we can now use a replication origin to track our progress, to tie this transaction to the source transaction and progress like this. And what we are, the end result is this pool table in which we store the payload as generated by WAL2JSON, as well as a bunch of metadata. This metadata allows us to keep track of the source database and the original commit timestamp and when the row was inserted. The last part is a replayer. So we have only one replayer process per target database for multiple source databases. And this one is quite simple also. We use the source database to set the correct search path, to use the correct schemas, so the database-specific schema as well as public for every extension functions and things like that. And based on the payload we saw earlier, we rebuild insert, update, or delete statements. Also, this replayer takes care of propagating DDL. On the source database, we set up an event trigger. This event trigger will log schema modifying statements into a special table, and at replay time, instead of replaying the content of this table, we will apply the DDL to the target schema. So this needs a bit of special care when writing migrations, because we have to make sure that every migration can be played using the correct search path. So we have to avoid using qualified names in the functions and things like that, and let the search path resolution mechanism to take care of that for us. No system would be complete without monitoring. Monitoring is always really important. So how do we detect failures? We have PG replication slots on the primary server, which track the replication lag. And the spool table size reflects the replayer lag on the target database. Based on that, we can set up alert in our monitoring system to know when something goes wrong. On top of that, we are working on a business metric, something that's not quite as interesting in terms of alerting, but which is important to give business some sense of what is working well with our solution, which is a replication lag. So to know, in average, how much time does a change from the source database take to be replayed on the target database. So the future is that we should land in production quite soon. We need a bit more intelligence on the DDL replayer side of things, because sometimes if the migration is not written perfectly correctly, we will have failures on the replayer side. We want to open source it, so this will take a bit of work to document everything properly, and, but sometime during the year it should happen. And maybe replace WAL2JSON with something different, because the JSON format is quite expensive to parse. Probably quite expensive to generate also on the source server. So if we can replace this component with some other logical decoding plugin, that will probably make us happy. Like I said in the beginning, in fact, it was quite easy to do that because the hard problems are solved by PostgreSQL itself, but some things were a bit more difficult than expected. Moving things from one schema to another is quite hard because they tend to grip everywhere. For example, when you have default values using a sequence, usually it's implemented as a call to next val using the sequence name as a constant value cast to a reg class, to a table name. And that's something you have to rewrite too, because it's usually qualified with the schema names and things like that. So rewriting this SQL on the fly leads to a lot of corner cases, things you have not intended and needs to rewrite, and you weren't really prepared for that. And the third problem we had is that we needed to be really careful about performance to be able to absorb a burst of activity on the primary server. Because since we receive the message only once the transaction commits on the source database, we tend to receive a lot of messages at once. And we want to be able to process them as quickly as possible to avoid any delay. On top of that, we had some issues with PostgreSQL itself. Event triggers are not an ideal way to propagate those schema changes, because sometimes it's quite hard to get the actual DDL statement being executed in your event trigger. And also some replication changes are weird. For example, if you write a DDL statement that needs to rewrite the whole table, like, I don't know, changing a column type, for example, you will get a lot of changes, like if you were inserting every row in a pgtemp table. But this pgtemp table doesn't exist on your target database, so it's quite weird to have that. Also, if you execute a create table as statement, you will receive the changes before you receive the event trigger notification that a table needs to be created. So in that case, you have table to insert somewhere, but you don't have the table to insert it into. So you have to be quite careful with how you write migrations with that, because of those limitations in PostgreSQL. So this project taught us a lot about how logical replication actually works, and I hope this can be useful to others. And if you have any questions, feel free to ask them, if we still have some time.